Fission and fusion, two types of nuclear reactions. So we're going to start with fission. Fission is basically when a neutron hits the nucleus of an atom. So here's where you see the uranium, it happening with uranium. So if we use that as an example, a neutron hits uranium, makes it unstable. So a previously like stable nuclei, and then adding a neutron to it increases the mass, which can therefore make it unstable. And once you do that, an atom will split. So what happens is when it splits in two or three different atoms that are smaller that sort of all make up the same mass as that original one, but they split and make smaller atoms. So that's kind of what you can see here. I know it's hard to see in the picture. The examples will be a little bigger. But here you can see the uranium, which got hit by a neutron. The uranium split into xenon. And does that say rubidium? I can't see. Anyway. So that's what fission is. It's taking a large nuclei and making smaller nuclei. The critical mass is the point at which the reaction can be sustained. So we do call this a chain reaction because when the atom is splitting, that's what these other little arrows are. They're neutrons that are coming off. So as it splits, it releases a few more neutrons. Those neutrons hit other atoms and so forth. If I didn't have those neutrons coming off, like if I didn't have two or three, however many, if I just had one and it just hit one other atom and then that atom released one, eventually that could sort of fizzle out, right? If that one neutron missed the next atom. So there is such thing as critical mass, which means we need a minimum amount of material to sustain this chain reaction, to keep it going. We can control it. That's how we do nuclear power, is we control one of these fission reactions. We do that with uranium-238. You can also use it in a bomb format. Actually, like nuclear bombs usually use a combination of fission and fusion. Let's see. When you break up the uranium into two or three smaller particles, if you were to go backwards and sort of add those smaller particles together to get the mass of the large one, you might find a little bit of mass missing. We call that the mass defect, and we can calculate how much energy that little bit of mass is going to give us based on the E equals mc squared equation, where c is the speed of light, m is the mass defect, so that little bit of mass that went missing, and then E is the energy. So that little bit of mass can give us a lot of energy based on this equation. Fusion does the same thing, where again we get a little bit of mass and it gives us a lot of energy. We actually get a lot more energy from fusion than we do from fission, and it happens at a instant. So when we use a nuclear bomb, we're usually using a fission reaction to start a fusion one. So in fusion, it's kind of exactly what it says. Like fission, you kind of think of fizzling out, like getting smaller. Fusion is taking those smaller ones and putting them together and making a larger atom. Nuclear fusion is how we make atoms in real life. Like there's man-made elements on the periodic table. We've done that through like fusion type reactions. They always form a heavier nuclei. They release, again, a lot of times more energy than fission. This is the process occurring in the sun. Again, we can also make a bomb. The hydrogen bomb is started by having a fission reaction that starts the fusion explosion. And we all hear about cold fusion. So fusion typically has to happen at really, really high temperatures. Hence, it happens in the sun. It also creates a lot of energy. So the idea of cold fusion violates that law of thermodynamics. And laws we know are proven and can't be changed. So there are four main types of radioactive particles. There are actually quite a few more, but these are the four that we're going to focus on. So beta emission. This is where a nuclei becomes unstable. And what happens is one of the neutrons, a neutron, it has a neutral charge. And in beta emission, that neutron splits. So when that happens, this neutron right here, this like blue dot, is going to split into a positive and a negative. Well, we know in the nucleus of an atom, we can only have positive. We can't have negative. So that neutron then turns into a proton. So it turns into something that's positive and it kicks out that negative. That negative that it kicks out is what we call a beta particle. So that's beta decay. Alpha decay is basically the nucleus of a helium atom. So if I had a nucleus and it lost 2 protons and 2 neutrons, that would be an alpha particle. This is the symbol for an alpha particle. Gamma is just energy, so it's not a particle at all. And then neutron is, again, when it releases a neutron. So it just releases mass. You can see here I have beryllium 13, and I went down to beryllium 12 because I lost a neutron. You'll see some more, or you'll see how to use that in sort of an equation format in the examples. And then finally, we talked a lot about like once a particle becomes unstable, this is when it's going to emit a neutron, or when the neutron's going to split, or we're going to have like a fission reaction. So how do we know? How do we know if like an atom has enough neutrons that it's become unstable, or has too few neutrons so it's unstable? There's like this very specific amount where it can be stable. That's what you see here in this picture. You see like this, what we call like a band of stability, where if you're in between this number of neutrons and this number of protons, like you're in this like green light area where you have stability, great. But if you have too few protons or too few neutrons or too many or too less or whatever, if it's not like a balanced amount, then we're outside of that band of stability, and all of those things can go through different types of decay. So neutron, beta decay, alpha decay. And I know this says positron emission and electron capture. Those are, remember on this slide I said we had 4 we were going to focus on. Those are other things that can happen as well. This is how we calculate if something is stable. So we're going to take the number of protons and then we're going to multiply that by 1.5. And if our number of neutrons fall within that range, then it's stable. If they're not within that range, then it's unstable. So I'm going to do an example, carbon 14. So based on the periodic table right here, I can see that carbon has 6 protons. And in hyphen notation, that 14 is the mass number. So we know protons and neutrons equals mass. So if carbon has 6 protons, then neutrons equals the mass number minus the protons, right? Mass equals neutrons plus protons. So if I just arrange that equation appropriately, my neutrons is the mass number, so 14, minus the number of protons, which is 6, which means I get 8. So here I just went ahead and put a 6 for protons. I multiplied 6 by 1.5 and got 9. And then I did my formula to find the number of neutrons and I got 8. This statement is true, therefore it's stable. If I did this and I got 10 here, then that would be unstable. If I did it and I got like 5 here, it would be unstable. So if this statement is not true, it's unstable. If it is true, it's stable. So that's how you can calculate if something's going to be stable or unstable based on the mass number. And that's it. So head on over to your digital notebook, and there'll be a few examples on there you can check out, but that's about it. Thanks.